Hello everyone, how are you all? I hope you all are fine and safe. Welcome back to Quantum Mathematics. I'm Aman, and today again I'm back with a very interesting video in which we are going to prove this infinitely nested pi representation. And uh, this was proven by I'm not sure whether I'm pronouncing his name correctly or not, but and this is known as VIETA'S product. Okay, so basically we are going to prove that. But at first, if you just have a look at this crazy looking thing, it looks ridiculously disgusting. I hope you can see that. But when you dive into it, when you just have some basic trigonometric formulas, so you're gonna see that this isn't that much tough to be proven. So let's prove it down. Okay, so firstly we are going to begin our journey with this formula that says double angle formula of sine, that says 2 sine x cosine x. Oh, should I prove this down for you guys right now? Okay, let me do that. So I can write this as x plus x, right? So there is a formula for sine of a plus b. It's sine of a times cosine of b plus cosine of a sine of b. Well, here are a and b both are x only, so eventually they are going to be add up with 2 and 2 sine x cosine of x, hence proved. So yeah, this is very easy to prove, but we are not here to prove this one, but we are going to play with this one. Okay, so I'm having sine of 2x as 2 sine of x times cosine of x. Okay, what about sine of x? If I'm just like taking the half of the previous angle, so I'm just gonna have 2 sine of x over 2 times cosine of x over 2. Okay, then sine of x can be written as, I can write this down as further using this formula. So when I replace okay, let me just have a look at that. When I replace x with x over 2, okay, let me just see that. Oh, sorry. Okay, so I'm looking for sine of x over 2, right? So let me just write down here. Sine of x over 2. Using the double angle formula, I have to take the half of this angle on the right hand side as 2 sine of x over 4 cosine of x over 4. I hope you can just imagine that, okay? And if I'm talking about sine of x over 4, so that can be taken as 2 sine of x over 8 times cosine of x over 8, right? So yeah, on the place of sine of x over 2, I'm just going to write the first formula that I have just evaluated soon, like right now. So that's going to be 2 times, oh wait a second. Yeah. So this 2 and times this one 2, and then sine of x over 4 cosine of x over 4, and then cosine of x over 2 was here. So this is like this part. Okay, this is like I have just like evaluated there over there. So yeah, this part sine of x over 2 is just 2 sine of x over 4 times cosine of x over 4, and this 2 like here, and this cosine of x over 2 is here. So yeah, and again I'm just going to open this sine x over 4 as I just did here. So that's gonna give us, I'm just going to write this down here, sine of x can be represented as 2 times 2 times 2 um, sine of x over 8 times cosine of x over 8 times cosine of x over 4 times cosine of x over 2. Okay, we are just playing with the sine terms, right? We're just playing with the sine terms instead of disturbing the cosine and all twos. So if you just if you observe this, like this one and then this one, then this one and then this one, so you're gonna have that sine of x. Just generalize it. Sine of x is 2 to the n, okay, times sine of x over 2 to the n, and times the infinite product, not infinite product, but as product as k goes from 1 to n of cosine of x over 2 to the k. Yeah, it's good. Okay. So when you just keep doing this n times, right? When you just keep just factoring sine of x over 2 with this formula. So when you do this n times, so that's going to be 2 to the n, yeah. And then sine of x over 2 to the n, the factor, and then all these cosines product. So that's going to be k equals 1 to n, and times cosine of x over 2 to the k. So when you let's play with let's say that our n is 3, right? So open this up to make sure that I just like generalized it correctly. Let me just cover it in a bracket. So sine of x is 2 to the 3, sine of x over 2 to 3 is 8, and the product as k goes from 1 to 3 of cosine of x over 2 to the 3. Oh, sorry, k. Okay, so when you just plug k equals 1, this appears, k equals 2, this, k equals to this, okay? Sine of x over 2 and 2 to the 3. Yeah, that's good. So this is our generalization of sine of x. That's really good. And if I'm not doing n times, but instead I'm doing this infinity times, so I have to take n tends to infinity, right? Let's do that. So take limit n tends to infinity. So like if you have studied or if you have like basic ideas about the limits of sine, so limit n tends to infinity of sine of x over 2 to the n would be just x over 2 to the n. So yeah, it's a basic like limits, okay? It's a basic limits. So I'm just going to replace it with that, right? Okay, yeah. So yeah, so I'm just going to replace when you take the limit. So I'm just going to take the limit as limit n tends to infinity 2 to the n sine of x over 2 to the n times the product as k goes from 1 to n cosine of x over 2 to the k. So when you take the limit, as I have just mentioned earlier, like here, so that's gonna give us, I'm not talking about 2 to the n, because if you take the limit 2 to the n diverges. So to just neutralize that, we are here 2 to the n within division. So we are just going to cancel this 2 to the n with this one. So we are just going to left with sine of x equals x times the product. Let's yeah, k equals 1 to infinity of cosine of x over 2 to the k. So this is your final result actually, if you just take that infinity times, okay? So now we are just going to play with this only, and when you plug, let's play with let's plug x equals pi over 2. Okay, so wait a second. So yeah, when you plug x equals pi over 2, so this becomes sine of pi over 2 over pi over 2, right? And well, by the way, it's known as Euler's sinc product that we just proved here. So when you just plug x equals pi over 2, so the product becomes cosine of pi over 2 to the k, and like sine of pi over 2 is this one, and this becomes 2 over pi equals, when you expand this, so we're gonna have, when you plug k equals 1, so this comes out to be cosine of pi over 4, just open this up, times cosine of pi over 8 times cosine of pi over 16 dot to infinity. Okay, yeah, that's good. And now we're just going to have a look at these formulas with taking in consideration the very good formula that says cosine of 2x is 2 cosine square x minus 1. Let's just simplify this out. Okay, so yeah, cosine of 2x plus 1 over 2 is cosine square x. So cosine of x comes out to be square root of 1 over 2 plus cosine of 2x over 2. So yeah, this is what we're going to use here to identify these all these stuffs. So when you plug x equals pi over 8 here, so that's gonna give us x equals pi over 8. That's gonna give us the square root of 1 over 2 plus cosine of pi over 4 over 2. So cosine of pi over 4 is the square root of 2. It means, okay, let me just tell you on the right hand, like that board. So yeah, this is really amazing. So yeah, just have a look at this. I'm just looking for like this, all these products. So when you plug, well, we know about cosine of pi over 4, that's the square root of 1 over 2. Okay. Yeah, the square root of 1 over 2. Okay. So we don't care about that. But we are like moving forward in consideration. Well, although it's correct, the square root of 1 over 2, right? So yeah, when you plug cosine of when you try to evaluate cosine of pi over 8, the next product that we have to evaluate, so that's gonna be 1 over 2 plus cosine of pi over 4 over 2. That basically comes out to be 1 over 2 plus 1 over 2 square root of 1 over 2, right? Yeah, okay. And now just try to evaluate cosine of pi over 16. So this becomes 1 over 2 plus cosine of pi over 8 over 2. And from the previous step, we can just plug pi over 8 like this one over here. So that's going to give us the square root of 1 over 2 plus 1 over 2, this one, and times the square root of 1 over 2 plus 1 over 2 square root of 1 over 2. And we are ready to just write the final result. So 2 over pi equals the square root of 1 over 2 times the square root of 1 over 2 plus 1 over 2 square root of 1 over 2 times the big square root 1 over 2 plus 1 over 2 square root 1 over 2 plus 1 over 2 square root 1 over 2 and dot to infinity. when you just plug cosine of pi over 4, this is cosine of pi over 4, this is cosine of pi over 8, and this is cosine of pi over 16. We have just proved here. That's easy. Like, it's not difficult, I think, because we have just proved this one. And if you have an idea about this one earlier, so you could do it faster. You could do it you could do it very faster. Like, it's easy. It just looks infinitely nested, something like disgusting, but yeah, it's love. Okay, I think I should write down here because okay, let me just write that down over here. So we finally proved the VIETA'S infinite product that represents pi, and that's really cool. So that is 2 over pi equal the square root of 1 over 2 times the square root of 1 over 2 plus the square root of 1 over 2 times the square root of 1 over 2 and times 1 over 2 plus 1 over 2 is square root of 1 over 2. Wait a second. Plus is 1 over 2 the square root of 1 over 2. Yeah, and this goes up to infinity. And let me guess the next product. So that's gonna be 1 over 2 plus the square root 1 over 2 plus 1 over 2 square root. Oh, sorry, here it's 1 over 2. So yeah, and then 1 over 2 plus 1 over 2 square root 1, 2, 3, 4, 5, 6 and 7. So this is your next product. If you have a look at the number of 1 over 2's in square root, so the first one is containing 1 only, second one is containing 3 only, I'm talking about the big square root, and the third one is containing 5, the fourth one will contain 7, and the next one will contain 9, so yeah, this goes up to infinity. That's really cool. So yeah, thank you so much guys for watching this video, and stay tuned for the next video because I'm just gonna bring the proof of Ahmed's integral. Like, that's really amazing integral. Let me just write that down here. Yeah. So the Ahmed's integral says, and yeah, it's gonna take a lot of time. Ahmed's integral is gonna take a lot of time because that's really difficult integral, I think. I firstly thought to just prove this down because I have soft copy of proof of Ahmed's integral, but then I thought to just prove this down with my handwriting way because maybe that's gonna take a time, but that's very efficient to understand. That's why. So that is integral from 0 to 1 of arc tangent of the square root 2 plus x square over 1 plus x square times the square root x square plus 2 dx. So this is the Ahmed's integral, and in the next video we are going to prove this down. Not prove, but we are going to evaluate this down, and the result is very fascinating. Just stay tuned for the next video. Thank you so much guys, and just have a good day. Goodbye.